Then, of course, there is the effective reduced or normalized pressure. It remains the same because we specially chose this representation for the pressure like that, just to keep the pressure without anything. So it will be quite easier. And also you see that in Coriolis storm the omega disappeared, but two characteristic value, Rossby number and Ekman number are appeared. And of course everything is equal 0, or maybe we can even shorten it just to take like that. And also of course there is a divergence of velocity field, which is also 0. And finally we should state the boundary condition. Boundary condition in the dimensional form we regard that the radius of the inner core of the is related to the radius of the outer core is related to the inner core like that, and it's of course equal not because it's rotated for the outer core with mantle. And then we have the boundary condition on the inner core, which rotate with a slightly different value, but nevertheless after this dimensionless transformation all this extra value are vanishing, and we have the for the inner core condition r equal 1, and this expressed just in sine square theta grad phi 2.5. Here this c coefficient which comes here is actually the ratio of radius of the spherical boundary and so called substantial derivative. So actually this c, it's necessary to stress. Okay, I don't know. Maybe here I wrote c is equal outer boundary to the inner boundary. So we are using the radius of the inner boundary as our initial variable of the distance, estimation of the distance. So of course at this inner boundary we have the radius, dimensionless radius is exactly 1, but at another boundary in which we rotating, and this is actually radius of the boundary between mantle and inner core. Oh, sorry, so between mantle and not inner core, but the fluid outer core. And so it's actually the value which about 2, because there are not 2, sorry, it's value about 6 because it's value about, so here we have the outer boundary at 3,500 kilometers, and here we have the radius of the inner core about 1,000 with something kilometers. So this is ratio is about 3, slightly less. Sorry?
P star. Please, sir. Yeah. Sir, the density will come, sir. P star.
P star.
R star. Density.
Density is already aggregated here because we divided on the density. So we in the initial equation we divided on the density. So density already didn't appear. So we this initial system. Okay, about substantial derivatives, I already told you. Okay. Okay, maybe it was to write down, but nevertheless, I think that it's clear that substantial derivatives is a combination of the ordinary derivatives in time and v times grad, which then acting on v again. So it's quite clear. And the small Ekman number E, which is written here, and the small Rossby number epsilon, set the most important similarity criteria in the deep interiors of the planet. This is actually we reduce the problem just to the two parameters. This is the epsilon and Ekman number, so we reduce just the two parameters. And the Rossby number is determined by the ratio of characteristic velocity of the flow to the characteristic rotational velocity of the entire system. So actually we can proceed to the definition of the these important numbers which control everything. So epsilon actually in our case is equal, okay, I'll write it somewhere here, epsilon just by definition in our case is equal b star divided by omega r star and we can also estimate it in the same actually way using our another variable. If we take the rotation, then we have omega star. Oh, okay, maybe. Sorry. Okay, this one, yeah. So then we have this relation of omega star to the omega itself, and this is quite for the Earth quite small number. It's much less than 1, and for the Earth this epsilon is about 10 to minus 6. And this parameter is very well estimated for the Earth, so it's about this value. So it's really too small, one over the million. And the next parameter, which is quite important, is the Ekman number. And the Ekman number is determined by the, okay, sorry, yeah, I just returned that actually Rossby number, let's write here, Rossby. Yeah, this quite important parameter which relate actually the relative velocity to the rotation. And rotation, you know, the real rotation with which Earth is rotating. As I already told you, in our case, the relative velocity just to 10 to minus 4 meters per second, while this real rotation rate is about some 100 kilometers per second. Oh, no, not exactly 100 kilometers, I forget. So it's okay, it's 10 to minus 6 into 6. Not kilometers, meters of course, 100 meters per second. 100 meters per second. I mistake, it's kilometers. But nevertheless, it's very big, and especially compared with that. By the way, this rotation, the real rotation of the Earth, can have even effect on the gravitation. You know that near the equator where this rotational effect is the most pronounced, we have very sufficient, I don't remember exact value, but some promiles or something of the initial, even up to the 1%, something like that. And of course here there is a tremendous effect because it's 10 to minus 6 this relation, and there is a very strong influence. And the Ekman, the next number is the Ekman number, is determined by the ratio of characteristic value of the viscous force to the Coriolis force. And it's also quite easily can be seen. We divide the viscosity coefficient, kinematic viscosity coefficient, more precisely to say, on the characteristic value of, again, the angular rotational rate, real angular rotational rate, and then it's multiplied, if you see, by the square of the typical distance. In this case, it's the radius of the inner core. And actually, we related this both, and then you see that again much less than 1. But here situation even more dramatic, because for the Earth this epsilon, if we consider the real molecular value, which is possible not only to identify somehow with seismic wave and so on, but even it's possible to make in the experiment. They use, doing some special experiment, they blow some stuff, and this blow, during this blow we have this extremal condition which happens in the Earth core, and so and they make very quickly measurements, and they found this viscosity is extremely small, that correspond. Of course, this value is well known and fixed, and this viscosity we can estimate, and it will give Ekman number 10 to minus 15. So its extreme value is so extreme value that it's almost impossible to reach with the model of the computer. Frankly speaking, that it's 10 to minus 15, and it means that if you to resolve just one computer step, you need to calculate 10 to 15. It's impossible for any computer now. But people who are in some sense, especially recently, quite successfully modeled the geodynamics and planetary dynamics, they say that it's not molecular viscosity we are using in the real situation, but turbulent viscosity. And for turbulent viscosity, this slightly going down, and it becomes on the edge of the axis of the computer. So it's 10 to minus 8, 10 to minus 6, something like that, for turbulent estimates. This is turbulent. Somebody didn't really believe in the turbulence, but maybe, yeah. But nevertheless, the result of the computation, which basically even reach 10 to minus 6, usually they in 10 to minus 5, 10 to minus 4. There are only particular examples of the calculation of the supercomputer even at this end. But nevertheless, they are quite successful in modeling and for the planetary dynamics and convection as well. But actually we will go another way. And the fact that the epsilon is extremely small, less than 10 to minus 8 in the Earth's liquid core, correspond to the low viscosity value in the main volume of the fluid layer under consideration. So in fact, it appears to be that this effective viscosity is very small, even in this case, when we consider the turbulent viscosity, it's also small. But nevertheless, there is some hope of the progress in this field. And it seems that we finished. So we finished a little bit. And so if there is any question, please ask. Is there any question?
Before that, moment of question. With the pressure. Here, pressure.
Which question?
2.4. Here, 2.4. So the right hand side is dominant.
So what?
That 2 terms. Additional pressure.
Yeah, there is a strong domination of Coriolis term. Very strong, and it's dominant very extremely. And first of all, it's compensated by the pressure.
Pressure.
So the pressure, first of all, compensates the Coriolis term. There is one important thing, because the Coriolis term is very important, but it's not produce the work. It cannot. It just cannot produce any work. So it's not creative term. It's just distributed. And first of all, it's compensated by the pressure. Yeah, and the only tiny amount remains from the Coriolis force, which further play important role for the pressure. But it's come as a surprise, but perhaps the most important term in this case is the viscous term. One can think that because the viscous term is multiplied by very small variable, very small Ekman number, so it's important, but it's not true, because actually it contains the highest derivatives, and so it says that we cannot omit it at all. We should regard it, and especially in the boundary. So it's dictate all the boundary condition and so on. So it's a very important term which you never allow to remove, while it seems that it's small. Yeah. And this is exactly the way we are solving the problem, because we're using this advantage of the. So we're using the advantage that this Ekman term should be kept somehow. And so it's reduced the problem from the problem in the full bulk of the core, but it's reduced to the problem to some boundary layer or shear layer. In this case, we have a very important boundary layer, Ekman number. In one lecture I will be case, and also some shear layer appear. First of all, on the tangent cylinder. Yeah, because they also very important. So you reduce the problem, roughly say, from three-dimensional space. You reduce it two-dimensional. You consider just boundary and shear, and you match them. So it's sort of the trick which allows to reach some asymptotic or even analytic solution.
Analytic solution by reducing three-dimension to two-dimension.
Yeah. But eventually, even this two dimension is reduced to one dimension because it's described by such a. So eventually, this three-dimensional problem in partial derivatives is actually 4 components, because there is a 3 component of velocity, there is the pressure, so it's 4 component. So it's contains actually 4 equation and partial derivatives. Finally, it reduces just to one ordinary equation, and even non-dimensional, but with many parameters which allow to match all these layers. Okay, so it's sort of the advantage, but it's sort of the art. Yeah, you find that all these are properly shifted, all this boundary, and all this layer, all this stuff. So it's quite interesting and quite.
So that is not applicable for other planets.
Yes.
Only for
The other planets. Yeah, it's other planets and even moons, larger moons, if they have a convection. Inside of them, so it's quite applicable. Yeah, please raise your question.
Yeah, ask a question.
Yeah, please.
It can applicable for stars also.
Hmm?
It can applicable for other stars also.
Yeah, it's possible to apply to the other stars, but difficulty, because this simple way that we regard that divergence is equal naught is for the Earth it's okay. With a good accuracy we can suppose so, but for the stars this compressibility is very high. For example, in the Sun we have a change in the density from the. Of course, we can consider, maybe you know that all stars, and especially our Sun, have convection zone. So the upper 1/3 of the volume of the star, upper 1/3 is convective zone in the Sun. And across this convection zone, if we come from the top boundary of the convection zone to the bottom boundary, so we have a change of the density in 7 orders of magnitude, 10 to 7. Just imagine, it's tremendous compressibility. So it's very high. So these things should be taken into account. But nevertheless, there are some approximation, anelastic approximation, almost asymptotic, almost adiabatic, approximation, which allow somehow to manage it. But still, there is no any at all model which can regard all this compressibility in full. There are only models when they suppose some average density, but such a big jump is nobody managed it yet. We have no picture about that, but yeah, I showed you a lot of pictures about the internal structures. Now I hope that you remember. So first of all, this situation with the constant density and differential rotation of the inner and outer boundaries are related to the terrestrial type planets. Of course, first of all, to our native Earth and Venus. Venus is actually twins of the Earth, but the conditions there are quite different. And if Earth rotating very fastly, Venus is rotating more than 100 times slower. And then Mars, Mercury, and Moon, and even to the largest satellite of Jupiter, Europe, Ganymede, and Callisto. And maybe you know that they were discovered by Galileo, and can now be confidently attributed to this group, which is terrestrial planet by their moon. And since their internal structure has been fairly well determined after the flyby of spacecraft near them in the 70s and 80s. Surely, and now it's 90s and 20s, and so all this flyby are proceed, and now we have very detailed picture of all this moon. They are indeed, some of them even greater than our moon. So, and they, and maybe the most active of them is Io. He has even own volcanic activity. And it's interesting that convection in Io could be controlled not by thermal effect, by maybe gravitational effect from the Jupiter mainly. So they, of course, eventually it's also thermal because this gravitational energy transferred to the thermal energy, but it's a very tricky way of transformation, quite different from Busse. So surely there is largest satellite of Saturn, Titan, which is the largest among cold satellites, which is the only one of all the satellites known to us that has a sufficient dense atmosphere. Also belongs to the terrestrial planet, this satellite, and it is very likely that this group also includes very large satellites of Neptune, Triton, and a slightly smaller satellite of Uranus, Titania. And of course we can speak about the exoplanets, why not? Because there are, I don't remember exact figure, but some thousands of them are already discovered, which are similar to the Earth in some sense, to the terrestrial planets, so that can work here. So all this has very wide application. Again, I should stress that we are first of all considering the application without any other influence. We only consider the influence of the differential rotation of the boundaries, because it's interesting that this problem could be solved actually exactly in asymptotic sense. And it was Stewardson who solved this problem. It's quite classical problem. And so it has very interesting flow. And so actually we now try to understand how it's works. And first of all, we, as we already stated, we consider the similarity criteria and geostrophic flow, and so it's the place to start this problem, which is in this chapter. Of course, we start from the initial equation. From the initial equation, they are written down here on the board. You see, we already discussed this equation many times, so I will not return to this discussion. And so actually this 2.0 or simply 0 inside this chapter, this equation, and you perfectly know all the notation, so I will not repeat them. So, and as the initial hydrodynamic equation defined the simplest model of such a fluid core of the planet, we use equation 114, and now it translates to the equation 20, and it with the complementary absent external forces F0. If you see there is F, no any F here. So because we actually consider the case when everything is driven by the boundary condition. Also for simplicity, we assume that the rigid outer boundary of radius RO out, it was shown in figure 4, and rotates with a constant angular velocity omega. This is exactly the angular velocity omega under which the mantle is rotating. And the rigid inner boundary of radius Ri, we also consider the radius Ri for the inner boundary, which I showed you in some previous slide. And it can rotate with some arbitrary angular velocity omega I. So there is a difference. So we have this picture, you see. There is a mantle here. This is mantle. Actually, in some sense, we show this some average terrestrial planets. But of course, in Earth, the mantle is much more pronounced, and it's up to this size. So it's the main things which control everything. And there is also here, I show you the liquid core and the solid core, and there is the inner radius Ri and Ro. And as I already said, that the the outer core is rotated with a solid body rotation and with omega O, and the inner core is rotated with omega I. And then we believe that the inner solid boundary can only rotate in azimuth, or other words, along the unit vector. Of course, this unit vector, again, I stress that it's the gradient of z, expressed, not z, sorry, it's gradient, it's unit vector in direction of azimuthal direction. This was one azimuthal direction which we rotate around the inner core or inside the outer core. So we can, now we have different angular velocity on this outer side. So we just denote this omega O, and inner side we have omega I. So there is a difference, namely this difference produces the flow. And so it's a rather interesting flow. First of all, we consider the most simplest feature of this flow, and then we proceed to more complicated features, which was discovered by Stewardson. And then anyhow, this problem couldn't be exactly resolved. And then, so therefore, also, okay. Okay, again I stress that all these boundaries are rotated with constant angular velocity, but different. And all these angular rotational velocity vectors are directed in one direction, which is, of course, in this case, the direction of the rotation. And actually, this is direction to the corresponding geographic poles. Here there is the north geographic pole, and here there is a south geographic pole, which is related to this rotation. And to the very high accuracy, of course, we can state that both of this velocity are in this one z direction along which they are rotating, and there is only small difference between the rotational rate of that and that. So therefore, also for simplicity, we assume that the rigid outer boundary of radius RO, see this picture, rotates with a constant angular velocity omega O, and the rigid inner boundary of radius Ri can rotate with the same some arbitrary angular velocity omega I. So it's different. So these two velocities are different, but not in direction, only in the value, and it's this small differential rotation. So therefore, two vectors of six-scalar non-slip boundary condition. I just remind you that there is six non-boundary conditions. So there is two boundaries, and on each boundaries we have the velocity, which is exactly correspond to the rotation of this boundary. So we have two boundaries, and each boundary we have three components of the velocity. So in fact we have six boundary conditions. And so the boundary condition we can write down like that. So so we actually are resting in the rotating coordinate system directly, heavily linked with the mantle. Of course, we suppose that the mantle is in rigid body rotation, that it's rigid, and so this corresponds to the rigid body rotation. Okay, so maybe I will write down again the most important equation for you. First of all, of course, the equation which we have is equation about the initial equation, Navier-Stokes equation actually, and also there is a divergency condition, and perhaps I will not write down this stuff because the only news here that the external forces F is absent here. So you just suggest that maybe you can write down to you that the initial equation for our case is just without this F value, which is the external force which can be acted. So let's consider more interesting equation which we didn't solve yet. And this equation related to this relation. It's necessary to write down, of course. Where is my chalk? I lost my chalk. Where is it? Oh, sorry. Thank you. Okay, so we have this simple relation that zero equation already told you that you understand how it looks like, so you can write it down right now. But if we consider the equation for the boundary condition, then we first consider the outer boundary. At the outer boundary, so we can denote this outer boundary like that. R equal R naught. So we suppose that we are exactly at this rotating system connected with the mantle. So the outer boundary condition for the velocity, for all three components of the velocity, is 0. And of course, it's important to note that it is vector. And so this is vector, and we have boundary condition of this point. But for the inner boundary, so we again have the same V, but in another place we have inner boundary with R equal Ri. And here we have also simple formula, but nevertheless a bit different. We have omega I minus omega O here we have actually the cylindrical radius, but because we are express everything in spherical coordinate, we will write down this stuff via the spherical coordinate. And of course, we are adding the unit vector. More precisely to say, here we have one r sign from this unit vector and another r sign we have from the distance from the cylindrical radius. So it has actually two components, this square. So eventually we have this boundary condition which is determine everything. And here we have made another simplification actually, which is entirely justified for the terrestrial planet. We believe that the inner solid boundary can only rotate in azimuthal, other words, along the unit vector. So just let me stress that it's along the unit vector. And this unit vector is, in this case, just r sine theta. And here there is Ri important. Ri sin theta. And here also Ri, because it's on the same boundary. In the system completely described by equation 0 and 1, by this equation, the only source of flow is the differential rotation of the rigid internal boundary. So there is a differential rotation of the rigid internal boundary because outer boundary is related to the coordinate system with which we are rotating. So in the system completely described by those equations 0, 1, the only source is this rigid rotation. I don't know. Oh, it's written here. Oh, sorry. It's rigid rotation, and this rigid rotation has a very simple form, and its source we can rename by the small omega I. Why small? Because actually it's really very small in comparison with the omega capital and this 2 omega capital. So the difference could be up to the 10 to minus 9. So it's tremendously small value. But nevertheless, it's produce valuable flow. And so it's omega I, which produce everything, is omega I minus omega O now, in our case. This is equation 2, 2. If this one omega I is not equal to 0, then and only then will the flow be maintained due to the viscous transfer on angular momentum from the rigid boundary to the fluid flow in figure 4 in the spherical layer under consideration. Otherwise, at omega small I equal naught, the fluid will simply rotate as a solid body with a constant angular velocity. Omega is equal constant everywhere. Okay, so we finish this paragraph. Let's proceed to the next paragraph. The previous paragraph was about initial equation and boundary condition, and now we start the next paragraph, which, okay, I just should change the PowerPoint slide for that. Okay. Seven, 8. Okay, so now in this next paragraph, we will consider in more detail the Earth's structure and Earth's magnetic field, magnetic field, Earth's hydrodynamic things. And this, in this chapter, we consider, as it stated here, you see, the characteristic value, Rossby and Ekman number. So we will consider this parameter, very important parameter. And of course, we consider the Earth. Here, all the characteristics of the Earth are written down. There is, as everybody knows, a solid inner core. Here, this solid inner core. And there is fluid outer core here, you see. And here, the most, in terms of volume and even mass, the most important thing is the mantle, which could be at our approximation regarded as the solid body rotating object, and exactly the system in which we are resting. So we have the radius of the Earth of this value, and there is a radius of the Earth which is slightly more than half of the radius of the full Earth. And also, let us agree here and further to designate characteristic value by a subscript with an asterisk. So further we will use this asterisk as the indication of the characteristic value here, here, and further on. So in the Earth fluid core, for example, the same characteristic value of velocity v to the star, this is very important thing, is about 10 to minus 4 meters per second. But of course there are some others, and I'm in the amount, who suppose slightly larger velocity up to 10 to minus 3. And so 10 to minus 4 is perhaps the lower limit, which is could be obtained from the geomagnetic variation. And but more coincide things which is connected with the energy processes in the liquid outer core is gives a slightly more difference. But in classical way, and especially in this way, when we considering the support of the relatively small differential rotation of the different core, this perhaps we for this, namely for this flow, we could go to the this lower limit of the velocity of the characteristic velocity, which is just 10 to minus 4 meters per second. So it is obtained both from the secular and modern analysis of geomagnetic variation and from the latest seismic sounding. It's interesting that it's possible to obtain this stuff also from seismic sounding, like you are using the similar sounding to discover the gender of your baby, which is still inside in your in your mother. And so the radius of the inner solid core of the Earth can be taken as a characteristic size. Here it's not written, characteristic size. About 1,000 with something kilometers. So it's about 1/3 of the radius of the fluid outer core. This is but just 1/3. This is quite tiny contribution, but nevertheless, as you will see later, it has a very strong influence, namely on this flow which we are considering due to the differential rotation of the solid in the core and mantle, actually. So accordingly, we obtain the characteristic time for flow in the Earth core. Characteristic time for flow in the Earth core, is it written here? It's written here, yeah. This characteristic time is about, if we just take the radius of the inner core, and then we take this 10 to minus 4 value, so this radius, this characteristic time becomes about 10 to 10. So it's roughly speaking, it's some hundred of years. Some hundreds of years, and its value as some hundreds of years is very, very well coincide with the observation of geomagnetic variation and so on. So it's some sort of the grounded things. And now we try to okay. And now we try to consider the characteristic value. To give a dimensionless form to a physical system, variables are expressed through characteristic quantities. And symbolically, in our case, such an expression can be represented in a way that comes from programming. So, further, we can write the general relation that we express radial, express the radius in terms of the characteristic value. So we actually replace the radius with characteristic value times the radius again. So we just replace that with that. And this is the trick which allow us to find very good the expression for the characteristic value and to get non-dimensional system. It's quite general things. Of course, we also expand in the similar way time. For the time we are reading the same things. There is a characteristic time and time itself. It's now become, after this substituting, like in programmer, we're not taking the equal, but we replace. And so this is a very effective trick to make the dimensionless in proper units, to make the system dimensionless. And so then again trick is with velocity is equal characteristic value and velocity not equal. We just replace. It's important. And then pressure. And the pressure for all these variables replacing are very simple because they itself are expressed in the similar value. The only difference is for pressure. For pressure, we have to take into account. We have to take into account angular rotational rate, so we can dimensionalize it. I just put it here. At least this is the most effective way to dimensionalize this pressure, in the way that we have typical length scale, then multiplied it by omega and multiplied by typical velocity. And here there is so this a bit more complicated, but of course we can say that this is actually p star, small p. Okay, this is formula 2-3. Actually, this formula is very general and it can be used not only in hydrodynamics but in any science where we have some differential equation. So it's quite effective formula. You just replace your variables which you are exploring with such a representation via the typical value and non-dimensional value. You put it there, then you collect all this typical value in some places, and this allows you to solve much more effectively the problem because you understand which terms of the equation are smaller, which are bigger, so you can manage with them. So this is a very effective tool. And also we can use the inverse value of omega because we have already typical value which is shown here in the previous slide, sorry. Because we have the typical value of velocity, typical value of the distance, which is, we coincide with the radius of the inner core. And so we have the typical time, but if we inverse this time, then we have the typical differential rotation. And this typical differential rotation, in our case, is of course typical V divided by typical R. And it becomes in second minus 1. For the Earth case, of course, first of all, we consider this stuff 10 to minus 10. per second. So this is inverse value. And this is the characteristic value of slightly differential rotation, to which we, for definite and fuzzy simplification, will fix in the second boundary condition. So this value we fix on the second boundary condition. From 1 to where is this? Okay, 1, it's written here, yeah. Okay. And also we regard this as a constant. We just suppose that this is a constant. And this is characteristic time. Inverse characteristic time, more precisely to say. And it's actually equivalent differential rotation. So characteristic quantities 3, 4, which I showed you previously, this 3, 4, are used first of all to reduce the original equation to a dimensionless form. Thus, with the postulated 3 replacement of R by the of R by R square R, T by T, T V star by T, V by V star V, and rho is by a bit tricky omega V star R star P. The system of four-scalar equation which was previously considered, and 6-scalar boundary condition is reduced. This is the problem. Actually, the way as we reduce, it will be the task for you. So, and this is the first problem. But here we just write down the result, and to the following dimensionless form we can reduce this equation. So it was to write down it. Let's write down it and comment. When I will write down it, I will comment it. So first of all, we collect all the small part in epsilon, which will be Rossby number, which we consider later. Then we have substantial derivatives, which actually include not, so this substantial derivative, let me expand it a little bit. It includes d over dt plus u grad no, not u, sorry. V grad, and it's act on V. So this is substantial derivatives, but maybe everybody knows it. First is the Rossby number, which we denote as epsilon because it's very small. Then there is even smaller Ekman number, which act on the diffusional term. So from the first sight, it looks like the diffusional term is not important, because here I just remind you, later I will say, the value, but nevertheless this usually for the Earth square 20 minus 15, while this epsilon is something about 10 to minus 6, 10 to minus 8. So it's so, and 6-scalar boundary condition is reduced to this. Let's write down the next term. The next term is Coriolis term. multiplied it by gradient z. Also the terrestrial planets. This group is formed by the planets and massive natural satellites that have a very similar internal structure. First of all, there are, of course, our native Earth, then Venus, then Mars, then Mercury, and the Moon, our great friend, also could have in the ancient history this convection. The largest satellites of Jupiter, Europe, Ganymede, and Callisto, discovered by Galileo, are now
Battery is over.